Hello students. In this video we're going to start a new chapter on colligative properties. Colligative properties are physical properties of solutions that depend upon the amount of particles that are dissolved in that solution. Specifically, the number of solute particles that are dissolved in the solution. And these properties are independent, that is, they do not depend upon the specific identity of the solute. It's just dependent on the number of solute particles that you have dissolved in solution. So those are called colligative properties. Now the first thing that we need to do in talking about colligative properties is introduce a new way of calculating a concentration of solution. And this new way is called molality. And I want you to notice here that it's not molarity, which we have discussed before, but it is molality, M-O-L-A-L-I-T-Y. So it's very close to molarity, but it's molality. As a reminder, molarity, which we have discussed before, is capital M, and that is the number of moles of solute that are in a liter of solution. And we've been working with molarity before in our solution stoichiometry and our dilution equations and so forth. So molarity is the number of moles that are of solute that are dissolved per 1 liter of solution. In contrast, molality is a little bit different. It is the number of moles of solute in the numerator, but the denominator is different, and notice what I'm going to write here. It is not liters and is not solution. Instead, it is kilograms. So instead of volume, it's mass. And instead of the whole solution, it is the solvent only. So it's the number of moles of solute per kilogram of solvent. So with this in mind, I am going to ask you to calculate the molality of a solution. And often that lowercase m is written in italics, so you can see that that's an italic m lowercase, contrasting that with a capital M for molarity. And we have to recall that when we see this, this is not m for mass, it is not m for meters. It is a lowercase m for molality. So we're calculating the molality of a solution of sodium chloride, NaCl, to 540 milliliters of water. And we're going to assume the density of water is 1.00 grams per milliliter. So with that in mind, I'd like for you to try this, set this up, and pause the video, complete this problem if you can, and when you're finished, resume the video and I'll work through the problem for you. Okay, coming back to this problem, we're calculating a molality, so it's lowercase m. We know that the lowercase m molality equals the number of moles of solute divided by the kilograms of solvent. The solute in this case is the NaCl. The solvent in this case is water. So let's start to plug in values. The number of moles of solute, I'm given 23 grams of NaCl, so I have to do a side calculation to convert from grams to moles. So I'll do that here. 23 grams NaCl. We're going to do a gram to mole conversion. Okay. So the grams of NaCl will cancel, and I'll have moles of NaCl. And then I can plug that in the numerator up top. Okay. Well, to get the molar mass of NaCl, I have to do another side calculation to figure out, to add up the atomic masses of sodium and chloride. Sodium is 22.990. I'll just do this on the side here. Grams per mole. And then chlorine is 35.453 grams per mole. And if I add those up, I get 58.443 grams per mole. So I'm going to now plug that value in here, as I have 1 mole equals 58.443 grams, right? So 58.443, so I'm going to take 23 and divide it by that number. And my calculator gives me 0.3935 and so forth, which I have to round it to sig figs, which is 0.39 moles of NaCl. Now I can take that number and I can plug that into my numerator right up here, right? Because that is how many moles of solute that I have. So I'm going to go ahead and plug that in to my calculation up here. 0.39 moles of solute. So now I need the denominator, and in the denominator I need the number of kilograms of the solvent. So it's the mass of the solvent in kilograms. So I can do a little calculation here. I start out with 540 milliliters of water. I'm given the density of water, so I can convert from milliliters to grams. So I'm just setting this apart from my previous work. 540 milliliters of water times this conversion of 1.00 grams per 1 milliliter, and that gives me 540 grams of water, which I could then take on and convert to kilograms, but also I can just shift the decimal 3 spaces, and so I get 0.540 kilograms of water. So again, I took the number of milliliters of water, converted it to grams of water using the density, and then I will convert those grams of water to kilograms of water by dividing by 1,000. Okay? So that then gives me my kilograms of water, 0.540 kilograms of water. Well, notice that this 540, this 0 is not significant because there's no decimal here. So indeed, this last 0 it should not be included. So I'll just go ahead and cross that out as a reminder that that is not included in my sig figs. Kilograms of H2O. Remember, we're just talking about the solvent here. This is the kilograms of solvent. So we've got 0.39 moles of the solute divided by 0.54 kilograms of the solvent. And when I do that math, 0.39 divided by 0.54, I get 0.72 as my answer. And my units here are going to be molal units. Molal. So it's 0.72 molal solution. Okay? And that's how we calculate a molality of a solution.